Oh, welcome guys. So today we're going to continue on our second part of the series on meteorology. We got last lesson we ended at number 11. So today we hopefully going all the way from 12 to 35. Hope you stay through the whole lesson. Don't leave. I see you. Okay. Well, I hope you've been keeping safe and self-isolating and all that shit. So anyway, let's continue from number 12 to 35. Okay, so we just take the bull by its own. So let's just dive into the question. So number 12, what is meant by an inversion layer? Okay, so an inversion layer. So obviously this deals with temperature. So we have three types of layers. So we have the normal one, and then we have the inversion, and then we have what you call inversion, not inversor, inversion, and then we have what you call the isothermal. So the normal one is the one that you know, it's a layer, it's a parcel of air, and we know that ordinarily as you go high, what happens to the higher you go, there very good, the cooler it becomes. I see you've been watching a lot of Dora. So the higher you go, the cooler it becomes. So keep that at the back of your mind. That's the normal way the atmosphere should operate. That's the way we call normal. So obviously the inversion has to be the opposite thing. So as the parcel of air is moving up, what happens? An inversion, the higher you go, the hotter it becomes. No, it's the opposite. The higher you go, the hotter it becomes. And then the iso means equal, thermal means temperature. Yeah, you see that? So for an isothermal layer, the higher you go, the temperature remains constant. Very good. So normal, the higher you go, the cooler it becomes. Inversion, as you increase your height, the temperature also increases. So the higher you go, the hotter it becomes. And this one, the higher you go, the temperature remains constant. So for number 12, we're pretty much done with it, because they're asking what is an inversion layer. And an inversion layer, we said it's an atmospheric layer, first of all, where temperature, the higher you go, the hotter it becomes. Where temperature increases, it becomes hotter with the increase in height. So the higher you go, the hotter it becomes. Number 13, what is meant by an isothermal layer? Isothermal, we said iso means equal, thermal means temperature. So isothermal layer is a layer of equal temperature. So as you go high, temperature remains constant because the whole column of air is experiencing the same type of temperature. It's an atmospheric layer with constant, so this is a key word, constant temperature with increase in height. Okay, so let's go to number 14. So number 14 is asking the temperature lapse rate with increased height within the troposphere according to ISA. It's asking for the temperature lapse rate according to ISA. So what is lapse rate, first of all? So lapse rate is what we call, so we know in an inversion or in a normal layer, the higher you go, a normal layer, the higher you go, the cooler it becomes. Yeah, so as you increase your height, your temperature drops. Yeah, so what that means is this, because you're increasing height and your temperature is dropping, or if it's an inversion, you are increasing height and the temperature is remaining, is going up. So there is a relationship at which you can represent in a graph form, in which maybe on the ground the temperature is 15 and then it drops at a certain rate up to maybe, so this is a change in height, and this is temperature. So you'll see this a lot often in meteorology. Temperature, not temperature, temperature. Okay, so you see you will see this sort of graph very often in meteorology. Yeah. So here's the thing. Yeah. Whenever, especially this will help us a lot in stability. So just listen. So as if it's an isothermal layer, if the temperature is on the ground is, let's say, constant, is here the temperature is 20. Yeah. So as you go up, mine is raw straight, so it should remain the same. Yeah. So that's an isothermal layer. The higher you go, the temperature, as you increase your height, the temperature remains the same. And for an normal layer, the higher you go, the cooler it becomes. It can even become cool until it goes to negative. It goes negative all the way. But for the other one, an inversion, as you increase your height, the temperature increases. So as you can see in all of them, you can have a trend and say the temperature is reducing at this rate per something. So that is what we call lapse rate. Lapse rate is a change in temperature per feet. Yeah, it can per height. The rate of change in temperature. That's what we call lapse rate. So in the International Standard Atmosphere, which we call the ISA, the lapse rate is given as 1.98 degrees Celsius per 1,000 feet. So that is the standard that we use in the world. That is given by, that's the ISA standard of the lapse rate. How the temperature drops as height changes. So if like here, for example, the temperature was 20 and I was at sea level, so if it goes to, and this is ISA, so at 1,000 feet high, if the temperature was 15 on the ground and the temperature is dropping at a rate of 1.98 for every 1,000 feet, so the temperature at 1,000 feet will drop by 1.98, and then we'll get the temperature at that level to be 13.02 or just 13. So this figure we can use it, some other people use it as 2 degrees Celsius per 1,000, just rounding off 1,000 feet. But also you need to know that you need to know that for the lapse rate, you see, like in the answers, you don't have 1.98 per 1,000 feet. So you need to know how to convert from one unit to another. Yeah. So for example, we know that the lapse rate is 1.98 per 1,000 feet. So this is equivalent to 1.98. 1,000 feet, we know that we know that 3.28 feet is equal to 1 meter. Yeah, 1 meter is 3.28 feet. So what about 1,000? It should be 1,000 divided by 3.28. So this answer you get roughly as almost 300. Yeah. So to simplify your work, yeah, whenever you see 1,000 feet, just know it's the same as 300 meters. So it's 1.98 per 300 meters. And when you see your answer is in meters, you just need to divide this side by 3 and this side by 3. And then this one you get 0.65 per 100 meter. This is your lapse rate. This is the same as this one. This one is the same as this one. So don't confuse. As in, you can cram this one, but it's fine. Well, I know you are capable. Yeah, I know you're very capable. But when you get to saturated adiabatic lapse rates. When you're dealing with stability, you have a lot of figures that you need to have at the back of your mind. So you don't need to stress yourself cramming all those and you can derive by yourself. Just getting if you know it in feet, you can translate it in the lapse rate in per 100 meter. Yeah. So number 14. Well and good. Clap for yourself. So number 15, which process may result in an inversion layer at about 5,000 feet? Very good. This is a very good question. Yeah. I think, yeah, it's a very good question. So what leads to an inversion layer? Because you're saying normally and then you're saying an inversion layer. So what leads to an inversion layer? Yeah, so it's very tricky. Yeah, it's not tricky actually. So there are only two things that can lead to an inversion layer. So one of them is ground cooling. Basically all of them are just ground cooling. Yeah, ground cooling during the night. That's one of them. And then on a high pressure area. High pressure area. Good. So those are the only two things that can lead to that's honey. I love my honey. Yeah, I love her. Do you want some honey? Anyway, ground cooling at night. That's up. High pressure area, ground cooling at night. So the only difference is at what level can it influence. Yeah. So like a low level inversion is basically caused by ground cooling at night. So in lower layers, actually what happens, you have the ground here. This is your ground. So the earth, obviously during the day, it heats up. It gets heat. Yeah, so it heats up. So once the sun heats up, not the earth heats up. Obviously it's a good conductor. Being a good conductor, it is heated fast, and a disadvantage is that it loses the same heat very fast. So at night when the sun just sets, heat is lost very fast from the earth's surface. Once it's lost, now the earth is cold. The earth is cool. Yeah. So the earth being cool, it cools the surrounding air, and the surrounding air has water vapor. Yeah? If it's humid enough, so there have to be conditions that have to be met. Yeah. So the nini, or what was I saying? It has to be a clear, cloudless night. So the conditions, we'll write the condition later, but let's just note this. So there is cooling of these water molecules, and then the cooling causes it can cause the water to fall below the condensation level, and then it forms fog or mist, whichever. So it can cause fog or mist, but we are not interested in the formation of fog or mist. We are just interested in the cooling. So the temperature might be cool even if it doesn't get to the condensation. So in the morning, the lower layers will be cool, but the higher layers in the atmosphere are warm. And here you are cold. So if you move from here to here, the higher you go, the warmer it becomes. So this is an inversion caused by what? Ground surface radiation. On our conditions are clear, cloudless night, so that the heat is lost by the earth. And then moderate winds. The winds have to be moderate. And yeah, that's it. And and for formation of fog, the air must be humid. But for normal, we don't care. We don't. Okay, so that's for number 15. So which process may result in an inversion layer about 5,000 feet? 5,000 feet is very high. Okay, so this ground cooling is near the ground, yeah? Near the ground, obviously below 5,000 feet. Below 5,000 feet above ground level. So height is above ground level. So be very wary of these terms, yeah? If I say an inversion at 5,000 feet and you know Wilson is 5,500 feet, you're like, hey, it doesn't even make sense. So when you say height, height is always, as in aviation, we mean the vertical distance from ground level. It may be 1,000 feet from Mount Everest, or 1,000 feet from Mombasa, or 1,000 feet from Nairobi, whichever. So it's just height above ground level. No go. Okay. So where were we? We were at that was the first one, ground cooling during the night. So the other thing that can cause we talked about it in the first ever video that I did on high pressure. Yeah, so if you want to refer to that, just go to the high pressure video, just indulge yourself in the wealth of YouTube knowledge. Okay, so high pressure area is this way, yeah? Because a high pressure is caused by this. I hope you're looking at what I'm drawing here. Subsidence of air, yeah? There's convergence at the upper levels, and then divergence at the lower layers. So this air is leaving slower. The rate at which it's leaving is slower, but the rate at which this one is coming in is higher. So if I ask, why is it the case? Because what do you have here? You have airports, you have people, you have cars, you have buildings, you have mountains, you have terrain, you have all those things. So for this to go at the same rate at this one, at which this one, the upper one, is coming in, it's very hard. It's very hard. Let's give him a break. It's very hard. So what actually happens is this. So there is accumulation of air here, and whenever there is subsidence, the air warms up adiabatically. So the air becomes warm as it descends. But you see, some of this, where this thing happens, high pressure regions are probably in the northern hemisphere. The land is usually, either whether it's sea or land, usually very cold. Yeah, so if it's very cold, you have layers that are constantly being compressed, and they are cold. And here, due to the subsidence, you have layers that are constantly getting warm and warmer and warmer. Yeah, so we have those two cases. We have those. So above 5,000, it is high pressure area. Below 5,000, near the ground, it is ground cooling. Hey, what is Safaricom telling me? Eh? Okay, so that's it. Okay, so below 5,000, ground cooling during the night. Above 5,000 feet, high pressure area. And remember, what you're talking about is height, yeah? Height and not altitude. So number 16, an inversion layer caused close to the ground. Now this one is close to the ground, can be caused by ground cooling during the night. Okay, so you have to differentiate between these two. One is above 5,000 feet and one is below. Obviously below is near the ground. So number 17, what is the ISA standard pressure at flight level? 180. So for this one, there's no trick, you just have to cram. Okay, so let me show you. So there's a table I usually give my students. But now, because you're not my student, so I'll not give you. No, I'm kidding. So this is it. So the table looks like this. It will not look like a table now, because I'm actually on top of the table, so I can't draw a table. Get the joke? It's a bad joke. Okay, so we have flight level. Flight. Horrible. So here we have ISA, standard pressure. So I usually have it from 5,000. Then I have 10,000. Then we have 18,000. Then you have 30,000 or 24,000. Then you have 30,000. Then we have 39,000. And we have 53,000. So these things, come on, this laptop has gone off. Okay, don't worry about that. So at 5,000 feet, the pressure obviously has to be higher. So for me, what I do, 30,000 feet, these are feet, yeah? 30,000 feet corresponds to 300. And then 1800, it's 200 more than this, so it's 500. And then 10,000 is 700. So you notice what happened there. So at 700 you reduce by 200, then you reduce by 300, like that. So you'll have your own way of cramming. This is how I cram. If you had respect for my knowledge, this is just crammed work. So the one obviously has to be 200, but it's not. It's 150. So the first one is 850. That's 850 millibars. These are millibars or hectopascals. So 850 minus 150, you get 700. 700 minus 200, you get 500. 500 minus 200, you get 300. But here we sorry, my bad. So here it's between these two, there's no 24,000. It should be 34,000. So here you should have 250, and then 34,000 corresponds to 250. So it starts from 850. 5,000 is 850. 10,000 is 700 minus 150. 18,000 is 500. 30,000 is 300. 34,000 is 250. 39,000 is 200. And 50,000 is 100. So you just need to cram, because they'll ask you any of this. Like here, they have asked you what is 500. 500 corresponds to what is flight level 180. So when they give you flight level, they've omitted 2 zeros. So it's flight level 180. So it's 180. Add 2 more zeros, so it's 18,000 feet. So at 18,000 feet, what do you have? 500. So my students, correct me if I'm wrong, but I hope I'm right. I don't think I'm wrong, because yeah. So that's it. So that's as simple as that. Yeah. So make sure you have that table at the back of your mind, At your fingertips, not at the back of your mind. Okay, so let's continue. Number 18. What is number 18 saying? Number 18 is, so they're asking pressure which is measured at a ground station and reduced to mean sea level. So I know you know these things. So for me, it's just simplifying so that you can remember for your exams. I don't care about your knowledge. I just care about your exam and passing and becoming a very good pilot. Yeah. So we have QFE, QNH, QNE, QFF, blah blah blah. We have very many of them. Yeah. So these these four, together with the S1 that is called SPS. So we have SPS, we have QFE, QFE, we have QNH, we have QNE, we have QFF, we have SPS. So QFE, what is QFE? Qualified Flight Extractor. That's so funny, by the way. So QFE is qualified. No, it's so cool. These things don't have meanings, by the way. So if no, they might actually have. They might be acronyms, but I don't know. Can't say that they are not. I can't say they are. So I just know that these are pressure settings. Yeah. Datums. They are datums that we use in aviation. So they are basically pressures. So some of them are pressures. I think most of them are pressures. So QFE is a pressure at an aerodrome. Yeah. So QFE is simply the pressure at an aerodrome. And where do we get that pressure at an aerodrome? Obviously from the weather point where we measure pressure, where the barometer is. Yeah. So that obviously the barometer might not be in the official elevation of that airport. Yeah. There are some airports that have very big difference between where maybe the instruments are and maybe where the height, there's big height difference between where the airport is and where the instruments are. So QFE has to be pressure at the official aerodrome elevation. Yeah. So it's the pressure at whatever that is taken at this where the instruments are, and then it's reduced to the, it is corrected for that factor. But simply, sorry, I've said a lot of things that actually I don't think made sense. So QFE is just what is QFE? Pressure at an aerodrome. Simple as that. QNH and QFF, pressure at sea level. Simple as that. SPS is standard pressure setting in ISA, or the mean sea level pressure in ISA. So the SPS is 1013.25. So for those of you who think that QNE is SPS, no. QNE is just the height that is displayed on your altimeter. It's just the reading that is displayed on your altimeter when you have set your altimeter to standard pressure setting of 1013.25 or 29.92. So it's QNE is a height. Don't make that mistake. It's not SPS. Okay? Yeah. So you said QFE is a aerodrome, is a pressure at the aerodrome. QNH and QFF are pressure at mean sea level. But how can all of them be the same thing? They are not the same thing. So one of them, the major difference is that QFF is a pressure at a ground station like an aerodrome that is reduced to mean sea level by prevailing atmospheric conditions. So you just use the conditions that are prevailing you get the temperature at the pressure at Wilson. If you want the pressure at mean sea level, you just do what? Reduce the pressure at Wilson using the prevailing conditions to get the pressure at mean sea level. But QFF is the same. It's almost the same thing. QFE, QNH, what? So I was explaining QFF. QFF uses prevailing atmospheric conditions to reduce QFE, to reduce pressure at a ground station to mean sea level. Yeah. But QNH is a pressure at a ground station reduced to mean sea level using ISA conditions. So the major difference is this one uses ISA conditions, and this one uses prevailing wind conditions. So a lot of you are thinking, why are you telling us about QFF? And we have been flying, we've been only using QNH. QNH is the most important one. Okay, well, we are in meteorology, and surface charts, surprisingly enough, have QFF. Those readings that you read on isobars, those are not QNH. Those are QFF, my friend. Yeah. Okay. Number 19. How do air density and flight performance change with decreasing temperature? So, as a summary of this, we want to see how density is affected by all other factors. So, density. So, let's take an increase. What leads to an increase in density? So, obviously, pressure. Let's talk of pressure. If you want to increase density, what must happen to pressure? So an increase in pressure. If the pressure is high, the density increases. Okay, so the first one is, so when my arrow is pointing up, it means increasing. If it's pointing down, it means decreasing. Yeah, simple as that. So pressure going up, density is increasing. Pressure going down, obviously density will increase. So temperature, for density to increase, temperature has to reduce. So if you decrease the temperature, density increases. Okay. Performance. With increase in density, how do you expect the performance to be? Obviously, very good. So this one affects this. Performance increases with increase in density. So humidity. Or is it humidity? Humidity. So if the humidity is high, so what leads to, which type of humidity causes high density? Is it low humidity or high humidity? Just think about it and give the answer in the comment section. High humidity, yeah? Obviously, so humidity is the amount of water vapor in the atmosphere. So water vapor is lighter than air. That's a fact that you need to know. So if water vapor is lighter than air, when you mix something that is light and something that is heavy, what happens to the heavy one? It becomes lighter, yeah, because it's a mixture. It's an adulteration. Okay. So humidity, if you have less water vapor, the density is higher than when you have a lot of water vapor in the atmosphere. So the lower the humidity, the higher the density. The higher the humidity, the lower the density. Okay. Humidity, a low humidity leads to a high density. Don't know if the arrow is clear to indicate that it's a down on arrow. Okay. So we talk pressure, temperature, humidity. What else? So we can say altitude. There are things that maybe I've forgotten, but you'll remember in your exam. Altitude. So altitude is whether you're going high or low. So if you're going, note that pressure is the major factor that affects density. Yeah, it overrides any other thing. So for example, altitude, as you go up, as you go up, what happens to the density? The density should reduce. So an increase in altitude leads to a decrease in no. So for altitude is this. A decrease in altitude leads to an increase in density. Why? As you decrease altitude, as you come to lower levels of the atmosphere, from up, as you come low, you come in and land to these lower layers of the atmosphere, there's high pressure here. High pressure leads to high density. Okay, so I think you need to know it is that temperature doesn't affect density that much. Yeah, temperature doesn't affect density that much as much as pressure, because as we go down, probably like at mean sea level, the temperature is high. I usually tell my students about Mombasa. It's a hot place with a high pressure. So we know that hotness lowers the density, because that's increase in temperature lowers the density. But another thing, pressure increases the density. But in an instance where you take your plane to Mombasa, the performance is very good. Why? Because the density is good. And then you'll ask yourself, why is it that the temperature doesn't affect the performance? It's only that for that case, the pressure, there is a large increase in pressure. So the pressure increase is 10 times more. The pressure effect on density is 10 times more than the temperature effect on density. Okay. Now, very good. We're moving on well. So let's look at number 20. Which process? So in our question, how does density and flight performance change with decreasing temperature? So if the temperature drops, what happens to the density? You have said if the temperature drops, the density increases. If the temperature drops, the flight performance. If the temperature drops, the flight performance increases. Obviously, decreasing the temperature. If the density increases, obviously the flight performance increases. The flight performance and density are correlated. Number 20, which process results in decreasing air density? What leads to decreasing air density? So there's temperature and pressure. You have to look at the answers. So which type of temperature will cause a decrease in density? High temperature. So obviously it's a high temperature will reduce. High temperature will High temperature will reduce. What was I even talking about? Sorry, I have to finish at 21. So high temperature will lead to low density. So what about pressure? Which type of pressure will lead to low density? Obviously, low pressure. So that's why the answer is increasing temperature and decreasing pressure. Yeah. the pressure at mean sea level in ISA conditions. So you need to know those ISA conditions at your fingertips. So like the mean sea level pressure in ISA condition is SPS, what I just said earlier. The teacher is tired. I can imagine how the students are. Oh, so the pressure is 1013.25, or in inches it's 29.92, or what? Yeah, those are just the ones that we use mostly in aviation. I can get away with that. So the mean sea level in ISA condition is 1013.25. Okay, so the height, so these are just ISA conditions, yeah. So for the ISA condition, I think you just need to know that for temperature, ISA conditions are given at mean sea level, yeah. Mean sea level temperature is given as plus 15 degrees Celsius. Pressure is given as 1013.25, or millibars, or 29.92 inches of mercury. And then density is given as 1.225 kilograms per cubic meter. What else? Lapse rate is given as, lapse rate is the rate at which temperature changes with height, 1.98 per degree Celsius per 1,000 feet, or this can be 0.65 per 100 meter. So the temperature of the atmosphere in ISA drops at 1.98 per 1,000 feet. So it's normal up to a certain height of 11. This is valid up to 11 kilometers. 11 kilometers is 30,090 feet. Yeah, 30,090 feet. I'm not sure. Yeah, I think that's the case. That's 11 kilometers. Yeah. So up to here, the temperature now remains constant. At minus 56.5 degrees Celsius. Yeah. So the pressure 21 we have answered is 1013.25. The height of the tropopause of the International Standard Atmosphere. The height of the tropopause. So the temperature remains constant. The lapse rate is 1.98 per 1,000 feet, and it remains constant up to the tropopause height. So the tropopause height is 11 kilometer, or 30 it's 36,090 feet. This is 36,090 feet, up to 36,090 feet. Sorry, I have to keep this pen here. So the height of the tropopause of the ISA is that. So in the answers, the only answer is 36,000 feet. So that's the answer. Okay. So number 22 is 36,000 feet. So the barometric altimeter indicates height above. So we have what we call the altimeter. Altimeter is what we use to get height on the aircraft. So I know you have learned about that in ATG. So there we have altimeter that you set. If you have been flying, I know you have set your altimeter to QNH every time, or you even tried QFF or QFE. So just have a glimpse of those things that we discussed earlier. So we have QNH. So if I set QNH, I get height above mean sea level. If I set QFE, I get height above the aerodrome. So this is what we call height above mean sea level, is what we call altitude. Height above the aerodrome is what we call height above the aerodrome. It's just height. And then if we set this SPS, standard pressure setting, we get height above mean sea level in ISA. So this one we call it pressure altitude, or flight level. Okay, that's it. So if we the barometric altimeter indicates, so a barometric altimeter indicates height above any of this, yeah, any of this. So the barometric altimeter indicates height above any of this. This is true. It can indicate, but when this is set, it can indicate height above the ground when QFE is set, height above mean sea level when QNH is set. So the true answer is the barometric altimeter indicates height above a selected reference pressure level. It can be either of these. It can be QNH, QFE, SPS, and so forth. Okay. So number 24 is asking, the altimeter can be checked on the ground by setting. If you want to check your altimeter, if you have to test your altimeter, if you have QNH, if I'm on the aerodrome and I put my QNH, I should get my height above mean sea level, which will be the airport elevation. So if you set your QNH, if you set the QNH on your altimeter, you'll get the reading that you'll get will be the airport elevation. So for like Nairobi Wilson, you'll get an elevation of 5,536 feet. So always have that anticipation. You'll get the aircraft. Don't wait for the ATC to give you. So almost anticipate, so that by the time you're given, you don't have to twist it so much. It's just fine tuning, yeah? Fine tuning. So this is QNH, because your altimeter may also have error there. So this is QNH. And the QFE, if you set your QFE, this is the pressure at the aerodrome. You should get 0. You should read 0 on your altimeter. Okay, so let's look at the choices for number 24. An altimeter can be checked on the ground by setting, it's either QNH or QFE, yeah? QFE, let's look at C, and comparing the indication with the airfield. Obviously, when you set QFE and you're on the ground, it will give you 0, so it will not give you the airport elevation. So QNH is the one that will give you, if you set QNH and you compare your indication with the airfield elevation, yeah? So the true answer is B. So just get that. Number 25, the barometric altimeter with QFE setting indicates. So if you set QFE, I told you we call it height, yeah? So obviously B is out. So if you set QFE, you've set the pressure at the aerodrome. So you'll get height above, not mean sea level, not standard pressure level. Height above pressure level at an airfield. So this one is correct. 26, the barometric altimeter with QNH setting indicates. QNH is height above mean sea level. We have discussed. So in case you need to refer to something, just go back to the video, pause, just refresh, and then come back to this question. We have already talked about them, so that's why I'm not paying keen interest on them. So given the following information, what is the true altitude? So for this one, you have to use the flight computer. So, and there's no way I can describe that here. I'll just have to show you later on. So just for number 27, we'll do it in the next class. So how can we, or I can do it separately and then attach the same. So look for number 27 at the end of this video. So 28, how can wind speed and wind direction be derived from surface weather charts? So surface weather charts are charts with isobars, yeah? Isobars. And we say the pressure there is QFF, yeah? So they're asking, how can you determine wind speeds? How can you determine wind speeds on a surface pressure chart? Simple. You just look at the isobars, how close they are together, or how far apart they are. If the isobars are close, it means the wind speed is high. If the isobars are far much apart, it means the wind speed is low. So for high pressure, we know that a high pressure system, the isobars are far much apart. So meaning the wind speeds in high pressure system is low. But in low pressure systems, isobars are very close together. That's why in low pressure systems you have very fast winds. Yeah. So how can the speed be determined? Just by looking at the isobars. So by alignment and distance of the isobaric line. So just check. Usually there is a scale for on the top left of an isobar of a surface weather chart. Yeah. So you just take the nini, you measure the distance, and then you go to the top left. You'll see a scale, and then you look at that distance. It will give you the speed of that wind. Which causes wind? Obviously, what causes wind? Obviously, there have to be a main. We know that wind flows from a high pressure to a low pressure. So first of all, before the wind starts moving, there has to be a pressure difference. So that's the key thing, pressure difference. The other ones, Coriolis force, centrifugal, those are secondary. But the primary effect, why we have wind flowing, air moving, then we call it wind, is a pressure difference, which creates a force called the pressure gradient force, which is the PGF. Yeah. So let's finish at number 30. Above the friction layer with prevailing pressure gradient, the wind direction is. So we are above the wind friction layer. and we have the prevailing pressure gradient. The wind direction is parallel to the isobar. How did I know? I didn't look at the answers. Because you have what you call the Bies-Ballot's law. So Bies-Ballot's law, this is how I put it simply. The Bies-Ballot's law is, so because I am in the southern hemisphere, you guys are in the north, me, I'm in the southern hemisphere. So what I use is this. So for Bies-Ballot's law is LLL. So what does LLL mean? So if the wind is flowing this way, if I look at the wind, so the first one is look, low, left. So if I'm standing here, I look at this wind, look at the wind, low pressure is to your left. So here is low pressure, here is high pressure. So they are asking, with prevailing pressure gradient, there is a pressure gradient from high to low. The wind direction is obviously, so this is the isobar. It's a high pressure isobar, this is a low pressure isobar. So the wind direction is parallel to these isobars. And it's to the left, it's coming towards you. But originally, the Bies-Ballot law states that with your back facing to the wind in the southern hemisphere, if my back is facing to the wind, so this is my head, don't know how to draw myself. That's basically how I look like, for those of you who haven't seen me. So with my back to the wind, low pressure will be to my right. Yeah, that's simply. But as simple as I explained earlier, this is the easiest way of remembering it. Yeah. Okay, so I think we'll finish there, and then next one will continue from 31 all the way to 50. Hope you enjoyed. Cheers, and do have a good corona night. Okay, so just do this.